Okay, everyone. So we are going to continue our day with the wonderful Colleen Farrelly, who is going to present a workshop applying topological data analysis that will overview persistent homology and the mapper algorithm from a theoretical perspective, and through exploring a dataset in Python with these methods. We're very excited to have you here, Colleen.
Thank you again, and I'm excited to go through this with you all. I'm going to probably switch back and forth between my presentation and coding. So let's get started with our first tool. So I sometimes get asked why topological data analysis. There are other methods out there that are a lot more common and have a lot less math involved. However, we have a lot of different types of data these days that can present a lot of challenges. So autocorrelations across time or space, any dynamic system can be viewed through topology. And a lot of the statistical methods really don't work. This sort of data breaks the assumptions. We also have really wide data. So one of the fields that I was in was genomics, and we might have 200 patients, but billions of genes that we collected. We might also have small data. When I worked in the education field, we had a lot of pilot studies where there might only be 30 students or 60 students. And we ran into a lot of problems with having a lot of predictors and not very many observations. Statistics just didn't work very well. There's also a need for visualization. When there's high dimensional data, it's very difficult to see what actually exists there or be able to break that down into something that stakeholders could understand. There's also just weird things that can happen with data that break the assumptions of machine learning algorithms or statistical models. So we have a need for these new tools to handle the weirdness that exists in real data. There are so many examples of tools in TDA. There's persistent homology, mapper, homotopy continuation, a whole field of things based on Morse functions. Euler calculus, discrete exterior calculus, Ricci curvature, mappings to Teichmuller space. I never thought I would see that coming up, but we actually do have those applications within the field of image analytics. So let's look at persistent homology for comparing groups and really extending hierarchical clustering. So our data either lives on a spreadsheet or it can live in its natural habitat, which is a point cloud. Each variable that we're collecting is its own dimension, and our data has a little address in this abstract space. And we can understand the relationships between these different data points by looking at the distances between them. There are hundreds, if not thousands, of distance metrics that I've come across, and each of them measures things a little bit differently. And so we have these really complicated spaces with points of data that can be measured in lots of different ways. And that's the starting point for persistent homology. Another key piece is simplicial complexes. So up here we have a graph where there are two-way interactions. This person right here is connected to other individuals in the network, but we don't have a way of really understanding, like maybe these three people are collaborating on a project together, and graphs just don't have the capability of summarizing that sort of a connection. However, if we look at a triangle of mutual connections, we now have a higher dimensional view of our data. homology is another key piece of this. So we can look at how many holes exist within a shape. So we can have a disk that has one connection and no types of holes. We can have a circle that has one connection and this nice little hole in here. Or we can have a soccer ball, or I think it's called a football where you are, that has a connection here. And we don't have circles in there, but we do have the void. It's empty inside. So homology and Betty numbers, these numbers that summarize the holes that exist, tell us something about the space that we're looking at. And when we put all of this together, we get the notion of filtrations and persistence. So we can filter distances or objects to obtain a series of objects. So we can obtain a series of graphs, we can obtain a series of simplicial complexes based on distances. And we can compute metrics of interest over these objects. So this doesn't have to be homology. It can be summary statistics or some other metric that we're looking at. And as we change these distances and compute these metrics, we can track how this changes across the full filtration of the data. It's a lot like an MRI of our data, looking at different slices and looking at what exists within each of those slices. And so putting all of this together, we end up with persistent homology. We can use our distance metrics to create something called the RIPS filtration, where we have pairwise intersections of distance-based circles or spheres or whatever dimension we're working in, centered at a point that connects it to other points within this point cloud or distance matrix. And so as we vary the distance for connecting points, we get a series of objects that are created from these different distance filtrations. We have a dimension parameter to look at how many holes exist. Usually the dimensionality is 0 or 1. The computation can get pretty expensive at the higher levels, and in practice, we usually don't see much of that in data beyond a Betty number of 2 or 3. There's a really cool theory that connects the 0th Betty number with a type of hierarchical clustering. So given some conditions, these are actually going to be equivalent, which is kind of cool to see how topology and machine learning really connect in this case. After we've computed these numbers for each of our filtrations, we can summarize all of this within a diagram. So we can visualize this, or we can apply some statistics to it to be able to really understand differences that exist between different point clouds that we're looking at. So we might be collecting surveys from different populations, or we might be looking at different images that were taken from a different type of object. And we can summarize all of this. And one of the cool things is once we have this in a diagram, we can actually perform math on the diagram to do these comparisons or to wrangle it into something that we can integrate with other data sources. There are a lot of implementations in R and Python. So we have a couple of R packages that do this and a couple of Python packages that do this, including scikit-learn, which can be really useful if you're getting started in Python and you're getting started in persistent homology. So let's look at an example with real data. So I created a small set of BERT embedded poems that are either humorous or serious in tone. And we want to understand if there are significant differences between BERT features between the two sets of poems. So BERT embeddings take text data and embed it in a context-aware model that they've created from a lot of training data. So it kind of summarizes what exists within the sample of text that's there. So we'll hopefully be able to get to this. Here we go. So first, we're going to import what we need. Our BERT embeddings are done with this sentence transformer package. So we'll run that. And then we need to get our data, which currently lives on my computer. And one of the things that we need to do when we're applying this deep learning method, this BERT model, is to fill any missing values so that it can fill these in. And we're going to separate this out into humorous poems and serious poems based on the type in the data set. That is not good. This had worked. It's maybe in downloads. Downloads, maybe. Yes, that is where it lives on my on this machine. So that seems to have loaded, and now we'll apply our sentence transformer and process this. It'll work pretty well on this. If you have a large sample size, this algorithm doesn't scale very well. But now that we have the embeddings, we can use NumPy to encode these in an array that we can then run through our persistent homology. So here we're using a couple of packages in Python, ripser and persim. And these allow us to do the filtration and be able to do the plotting. We're going to just use Euclidean distance here. You can create whatever type of distance metric that you want. I just decided to do Euclidean distance for simplicity. And then once we have these for our humorous and serious poems, we can apply this ripser and look at maximum dimension of 1. So we'll look at how many components exist and how many circles might exist in there within the distance matrix that we just defined for our poems. And that looks like I need to do pip install here. I have a new computer, so bear with me on what might exist and what might not exist on here. It can take a while to install some of these, but hopefully this will work. So it looks like we were able to get this in and run our persistent homology. Next, we can compare these different types of poems and what their persistent homology looks like by plotting the diagrams. Hopefully that... It never fails. Whenever you demo code, it seems like everything always breaks. Oh, it looks like my computer does not like this. Let's see. I'm sorry about this. This was not able to install on my machine. So I think I'm going to not run the code on here. There's something with the new Windows that doesn't seem to like this module. So I'm sorry about that. The diagram disappeared, but you would be seeing a plot that has different colors within the diagram that shows where the features live relative to each other. I'm going to try to not run this so that nothing else breaks with not installing correctly on here. I don't know what's going on. I ran this before and it worked. After we have the features defined for persistent homology, we can use this bottleneck distance to find the distance between the diagrams that we have. And there are a couple different distance metrics that we can use. The bottleneck distance is one that I like using. And here we see that this distance is 6.67-ish. But without context, we don't really know what that means and if there actually is a significant difference. So we can create a non-parametric test to look at the expected distances under a null distribution. So we can sample our poems from our humorous set of poems. So we have 10 poems in there, and we can run this code several times to get a distribution of scores. So we can do these 2 random samples of which poems we're going to look at. We can define our arrays and our distance metrics for both of those, compute our persistent homology for both of those samples, and record what the bottleneck distance is. From there, we can do our statistical testing. For this, we can use the 95th percentile for our confidence interval and figure out what that score is. If the score is higher than this, we're going to see that that's significant. If it's below it, it fits with our null hypothesis that there aren't any differences. And the value that we get here is a value of 15. Our value of 6 is lower than that. So it doesn't look like the context of our poems differ by humor or serious tone in the poem. Let's go back and look at our next tool, which is the mapper algorithm. So this can be used for clustering and data mining. This is based on Morse functions. So in a technical sense, there are a lot of conditions that need to be met for a function to qualify as a Morse function. But essentially, when we meet these conditions, there's a height of sorts that's defined. We have a function with different values that can be higher or lower that's applied to our data set. And in here, we have critical points where things are at a maximum or a minimum or an inflection point. And at those critical points, the behavior of the function changes across our data set. And we can kind of break things down based on the minimum, maximum, and these inflection points to understand different parts that exist within our data. From there, we can look at nerves, which are open coverings across data. So we can summarize what exists by covering certain values with this covering. So imagine that we have a data set with different values in here, maybe our sine wave example, and we can cover different parts based on the critical points that exist. And from there, we can summarize where things are different across our data. And we can summarize this with these little points or these little values that stand in for the group that's being covered. And this gives us a nice summary of our data. And we can play around with how much overlap there is or how many of these coverings exist. Here there's 3 of these and there's some overlap there. But we could make this more stringent. We could have less overlap. We could have a lot more values that we want to cover with this. Or we could go the other way and have a lot of overlap and not very many value sections that are being covered. So with the mapper algorithm, our first step is to project the data. So we take input data and project this to some sort of embedding. So some examples of this, we might put it into 3-dimensional space with PCA or a manifold learning algorithm. Or we might look at our k-nearest neighbor algorithm again and embed distances based on nearest neighbors. This kind of wrangles our data down to a nice usable size where we can create these functions and these covers. And one of the really important things with this algorithm is the cover parameters. So we look at the % of overlap across covers and the number of covers that we want to use. So you can kind of think of this as if you were trying to cover your couch with different sets of blankets, how much do you want it to overlap? How many do you want there to be? You're going to get different covers covering your seat cushions or other stuff that you have on your sofa. You're going to have different results from that based on how you want to cover your sofa and how many blankets you're putting over it. It's the same way with data. These are the really important parameters. Depending on how you embed it and how you're looking at different pieces of it, you can get very different results. From creating these covers, we then apply clustering to see how all of these pieces kind of get put together into groups. And we can save the model output with some of the tools that exist to get a really nice visualization of what's going on in our data. So we have R and Python implementations. I'm going to avoid actually running the code in case there's other packages that my new machine doesn't like, but we'll go through how to do this in Python. We're going to use the same example of our poetry set to be able to cluster poems and understand what subgroups might exist within each of these sets of data. So let's dive into Python. We're going to use the K-mapper algorithm and our sklearn package to look at our clustering. So we load our mapper. We define a transformation of our data. Here I'm using k-nearest neighbors distance for embedding with 3 nearest neighbors. It's a really small data set, and changing the parameter changes the smoothing. So a smaller value for a smaller data set is usually good. If you want a lot of smoothing, you can use more. You can use a higher number of nearest neighbors. And then to run mapper, we have our projected data. We have our original data. We have our cluster defined. Here it's dbScan, which is a density-based cluster. It has its own parameters, and those can be optimized. And then for this example, we're going to use a cover that where we have 5 covers and we have about a third overlapping. And using this function, we can visualize it. I'm not going to run it here, but here's what it looks like for our humor poems. We have a lot of distinct values here and not a lot of connections between those values, which suggests that we have a lot of variety within these type of poems. We don't have a lot of connections between what exists in this set of poems. We could run this again with our serious poems. I had planned on doing that, but I think it's going to break. When I was playing around with it, I did find more connections with the serious poems. So there were a lot of lines connecting these different groups, suggesting that there's a lot more overlap of the content that's in those poems than there is with our humorous set. So this can be really useful for understanding what exists within the data and how big of a problem subgroups might be. If there's a lot of connections that you're seeing, if there's a lot of lines connecting these points, it suggests that you have less distinct subgroups. And that means that if you're trying to model something at a population level, you're not going to have as many problems with your supervised learning due to subgroups. But if you have something like this, where a lot of these groups are very unique, it can be problematic in doing prediction. You might have subgroups that are very different or outliers that exist in your data, and it can be a good idea to really look back at your data before you're doing your supervised learning, just to make sure that nothing is going to bias your algorithm or average out something that might be really important. So say you're modeling a medical population. If you have a group of patients with an extreme version of your disorder, you really don't want to average out their contribution to the prediction, because it might be very important clinically. So this can be very useful with understanding the data before you start doing your modeling. Let's go back. I actually have a third tool that we can go through that I'm going to go through in R for those who are R users. So Ricci curvature comes up a lot in social network analysis, as well as analyzing biological networks or supply chain networks or electrical grid networks. It's one of the more useful tools and one of the newer tools in the field of network science. So when we're looking at spaces that are not flat and are typical axes with data existing on them, we can end up with some kind of weird things happening. So this is what we usually assume about our data. We assume that it's pretty flat. We can use a ruler to measure things, and the ruler isn't going to mismeasure certain parts of our data. But if we have positive curvature, things are going to be more spread out in certain areas and less spread out in certain areas. Same with negative curvature. We can see things spreading out towards the periphery and kind of squeezing in the middle, versus kind of puffing out in the middle and squeezing at the top. Understanding this curvature is really important when you're working with data. If you know that your data lives in, say, this space, you're going to need different metrics than if it lives in this space. And one of the key things with a lot of network science is finding important pieces of the network. So say we have an epidemic network or a power network, and we want to understand what's important for the disease or the electricity getting from one place to another. This is an extreme example of a network, but say we're interested in power getting to this area of a city, and what might happen if one of these other power stations were to have an issue. Maybe there's a natural disaster, maybe it's being targeted, a lot of things, or maybe there's just a mechanical failure. So where might we want to position our resources to make sure that the grid doesn't go down to some of these key areas? This central point, if we lose that, we're going to lose power to the other 5 stations. So that's a pretty important part of the network. And Ricci curvature is one of the more useful ways of finding these really important points within a network that's usually a lot more complicated than this toy example. So with this algorithm, we're going to calculate the curvature on the edges. So we examine each vertex and its adjacent edge to see how much stuff is kind of pulling it, how much is deforming it from what it would usually look like, or what our assumption of something that's flat would look like. We can pull it up, we can pull it down, we can squish it. Each of these edges and each of the edges and edges kind of contribute to weighing down the network. So once we have what's happening with the edges, we can sum up the edge weights around a vertex and figure out how much stuff is tugging on our vertex. And that gives us an idea of how important that vertex is to our network in general. Unfortunately, there aren't any packages for this, so this is something that has to be custom made. I used iGraph for this, which exists in R and in Python, so that this is generalizable. And the example that we're going to look at is a town network representing a supply chain. So it could be medical supplies that need to get from place to place. It could be food. That's been a really important one lately in the world with disruptions to the supply chain with COVID and some of the conflicts. It could be an electricity supply chain, so our power network. And we want to understand what vulnerabilities exist within that network to allocate more resources to the more vulnerable spots so that they don't go down and take down other parts of the network with them. So let's turn to R, and hopefully this will run. I've been using R on this computer, so I think everything should run on this one. We're going to create our matrix of 4 towns, and we could do a weighted network, but it makes the calculations more complicated. So we're just going to have, are they connected by a road or are they not connected by a road? So we run that. These aren't very descriptive town names, but they do help us distinguish town from town. So we'll label our matrix. And then we'll turn our matrix of towns that summarize their connections into a graph and look at that graph. So here's our plot of towns. We can see here's town 1, town 2, town 3, and town 4. From this, we can see that they're not all connected to each other, and there's probably dependencies. This town right here is probably especially vulnerable because it only has one way of getting supplies. So that's something that we'll look at as we look at different measures of how important each of these towns is to the overall supply chain. So we can look at degree, which degree centrality is looking at how many connections each vertex has. So this one doesn't have very many. This one tends to have a lot. And we'll look at that now. So as we can see, we have more connections from this more central vertex than we do from the ones on the periphery. Another useful metric is looking at betweenness. So we can look at the paths that exist to get from one place to another and whether or not they go through a given vertex or not. This can be important for understanding where some of the important paths are or which vertex has the most paths going through it. So we'll run that. And as we would expect, the only one that's important here is our connector. So we can't get from one side to the other without going through this town. Now let's compute our curvature. So we're going to look at our edges first. And when we don't have a weighted network, our Foreman-Ricci curvature implementation is actually a pretty simple formula that looks at the degrees within our network. So let's compute that. Now that we have that, we can sum up the curvature for each of our vertices by looking at which edges are around there and what their curvature is. So we'll run that, and then we'll plot this to see which towns are really important to this network based on our curvature. And here we see, as we'd expect, our central vertex is pretty important still, but we can see that we have these secondary connections that can help with the vulnerability. So our towns 2 and 3 also are important to the supply chain. Less so is this town 1, which is very dependent on the other areas to be able to get its supplies. So this can be really important for understanding problems like this of resource allocation and understanding vulnerabilities within supply chains or within even social networks of if you kind of took out some of these important players within a network, would the information fall apart? This has been used a bit in industry, but it's not that common yet, mostly within the context of assessing vulnerability within structures. So that's what I had. Sorry that the demos were a little bit short. I had hoped that I'd be able to actually run the Python code, but it looks like Windows does not like those packages right now for some reason.